Here's the equation at the heart of how machines learn to make good decisions. Take a good look, and if it means absolutely nothing to you, perfect. Give me a few minutes. With nothing but a hiker, a trail full of gold, and a few snakes, we'll build every single piece of it, until this whole thing reads like a sentence. Meet our hikers. We send a whole crew out across these mountains. Gold is the real prize, snakes to steer clear of, and a bit of ice cream for a treat. And every trip, they're scattered somewhere new. We hand every hiker the same guidebook. At each fork, which way to lean and with what chance. That one shared guidebook is the policy. Right now, every fork is a coin flip, 50-50. Send one hiker out and follow their whole trip, fork after fork, all the way down. That single path is a trajectory. This time, the hiker went left, then left again, and struck the gold jackpot, +10. But take the very same first turn and a different second, and the reward flips. This hiker meets a snake, -10. So here's the real question. Across the whole crew, every hike they could ever take, how good is this guidebook on average? That's next. A fork is a probability distribution over its two branches, left and right. Right now it's an even split, a coin flip. But the two aren't equal. The left branch is worth more. That's the way to the gold. The gradient points that way. Take a step along it, and that update leans the split toward the left, and the reward climbs. One fork. A policy is two numbers. How much you lean left, how much you lean right. 1 point on this floor. Lift each point up to the reward you'd expect there. The floor becomes a tilted sheet. Low over the bad policies, high over the good ones. Walk the left edge toward gold. It climbs by 10. Walk the right edge toward ice cream. It climbs by 3. Those two slopes are the gradient. 10 and 3, what's just the rewards? On the floor, the gradient leans toward the gold branch and points straight uphill. One rule, the two chances must add to 1. So you're stuck on this diagonal ridge. Follow the gradient along it, shift weight onto the gold branch, and the reward climbs from 5.1 up toward 8. That's the policy learning. A real journey is many forks, each its own distribution over left and right. On every branch, we read the partial derivative. Green, up toward reward, red down toward snakes. Together, they are the gradient. A real hike is a chain, your choices and the terrain's luck, where the gold and snakes happen to sit. You can't move the gold. The one thing you control is your chance of turning the way you did. So after a hike that paid off, nudge the probability of those turns up. That little push on the log probability of your choices is the log pi term in the equation, nothing more. And notice what gets touched. Only your choices, the blue ones. The terrain's luck is not yours to set, so it simply drops out of the math. Before we send anyone out, the payoffs. The real prize is gold, worth the most, +10. The ice cream is just a small treat along the way, +3. And a snake is a penalty, it costs you, -10. Add up whatever a single hike runs into, and that total is its reward. Now, how do we tell a good policy from a bad one? We send hikers out and watch. Send the hiker out. One full journey, one episode, one sample. This time down the left route. Along the way, a big pile of gold, +10. And an ice cream at the end, +3. 13 in total. A good hike, struck gold. Send another hiker. A second episode, sampled from the very same policy. This one heads right. You grab the gold, +10. But then, a snake, -10. Right back to 0. A wasted hike, same policy, wildly different result. 2 hikes, +13, and a big fat 0. On their own, useless. The reward swings all over the place. So we sample a whole batch of episodes from the same policy and average their rewards. Jumpy at first, but the more we sample, the more it settles. That settled value estimates how good the policy is. And here's the key. The exact same batch of hikes also tells us how to update the policy. Sample a batch on the left, and every fork split shifts on the right. Sample, update, over and over. That is the engine of policy gradient. We keep saying, a good hike, push its turns up. But good compared to what? Compared to the average. Take the whole batch, average their rewards. That line is our baseline. Now subtract it. How far a hike sits above the line is its advantage. Above the line, we encourage the turns it took. Below the line, we discourage them. And here's the catch. This hike found ice cream, +3. Positive, sounds good. But the average hike did better, so +3 is below the line. Its advantage is negative. So we actually push those turns down. That's the advantage, not the raw reward. And it's the last piece of the equation, the A. Stack every fork split together, and gradient ascent collapses the distribution onto the single best route, the gold. One bright river, one peak. Here it is again, only now every piece has a picture. The left side, how to improve the guidebook, which way is uphill. It's an average over hikes we actually send out and sample, added up over every step of the trip. The nudge, raise the log probability of the turns you took. Scaled by the advantage, how much better than average that hike did. Put it together, sample some hikes, and for each one, nudge the turns you took by how much better than average it did. That's the whole equation. And now it reads like a sentence.